You know that feeling? You're deep in the trenches building software. Maybe you're keeping up with the latest framework.
Yeah.
And then, boom, the whole conversation just shifts under your feet. Like yesterday felt like everyone was talking React this, React that.
Yeah.
And now, suddenly, it's web components, micro front ends, server-side rendering, performance, even like the time to first byte, it just moves so
It
fast.
really does. It's kind of dizzying sometimes. And it's not just the tech buzzwords changing either. The whole industry is, well, it's transforming.
How so?
You look at companies, say, in the Berlin tech scene, like N26, Zalando, Delivery Hero. Not so long ago, they were pretty small startups.
Yeah, relatively.
Now, they're huge public companies,
Yeah.
thousands of employees. And that kind of crazy growth, it's happening everywhere. It means the complexity we're facing as developers is just exploding.
The demands are definitely higher.
Totally. The game's getting harder, no doubt about it.
It really feels like just making the code work isn't, well, it's not really enough anymore if you want to stick around and have a future.
One of our sources actually put it quite bluntly, saying developers need to transcend just being coders.
Transcend. What does that mean exactly in this context?
Well, based on the source, it means, not just relying on memorizing specific APIs or library functions.
Okay.
It's about being comfortable stepping back, seeing the bigger picture, focusing on the patterns, the fundamental ideas that actually don't change that much, even when the specific technologies do.
Yeah.
Understanding that, yeah, making it work is just the starting line.
Exactly. And that right there, that's where the stuff we're really digging into today comes in. Software architecture and design patterns.
The big guns?
Pretty much. Because these aren't just like abstract academic things. They are the real tools, the foundation you need to build systems that can actually cope with all this complexity.
Systems that are robust.
Maintainable.
And scalable, yeah.
Okay.
Systems that can actually survive and thrive in this constantly shifting landscape.
Okay, so let's unpack this. For this deep dive, we've pulled together a whole stack of sources. We're looking at those industry shifts, the core ideas behind software architecture, how you even think about designing and evaluating systems, and then digging into proven solutions through design patterns with some real-world case studies to ground it all.
Right. And our mission here, really, is to go through all this material together, pull out the key insights, the most valuable bits, and give you, the listener, a really clear understanding of software architecture and design patterns.
Why they matter now more than ever and how they're actually used.
Exactly. So you feel informed, ready to tackle those bigger, more complex challenges that are definitely coming your way.
All right, let's start at the top then, software architecture. What is it, fundamentally?
Well, the sources define it pretty simply, actually. It's the result of the really important business and technical decisions that shape a system.
But those decisions aren't made in a vacuum, right? You've
Yeah.
hinted at that. There's a whole ecosystem influencing them.
Oh, absolutely. One source calls it the architecture business cycle, the ABC. It's a useful way to think about it. It shows the architect isn't just, locked in a room making purely technical calls.
They're getting input from everywhere.
Exactly. Like stakeholders, for instance. That's a huge one.
Yeah, this source had this image, right? Showing all the different people whispering in the architect's ear, basically.
Kind of, yeah. You've got management worrying about, cost, keeping people busy. Marketing wants features, fast time to market. End users, they just want it to work well, be fast, be secure.
And the maintenance team is thinking, please make this easy to change later.
Right. And the customer wants it cheap and on time. Their concerns are often pulling in totally opposite directions.
So the architect is kind of juggling all these competing needs.
That's a big part of the job. And it's not just the people. The developing organization itself is a major influence. Things like the company structure, the actual skills the engineers have on the team, the schedule they're under, the budget. These are hard constraints.
Yeah.
They shape what kind of architecture is even feasible.
Makes sense. And the architect brings their own baggage, too, presumably.
Definitely. Their own experience, past projects that went well or maybe crashed and burned, what they learned in school, patterns they like, maybe even just a desire to try something new.
And the existing tech environment must play a role. What systems are already there?
For sure. Existing systems, infrastructure, all that feeds in. And the ABC idea captures it as a cycle because the architecture you build then influences future requirements, future business goals, even the organization itself. It feeds back.
Okay, so given all those influences, what does an architect do within this cycle? What are the main activities?
The sources list several key things. Obviously, creating the business case for why the system should even exist.
Right.
Then really digging deep to understand the requirements. often using things like use cases or specific scenarios to really nail down what's needed.
Eliciting those requirements.
Exactly. Then, actually creating or selecting the architecture,
Yeah.
documenting it clearly, that's crucial.
So others can understand it. Yeah.
And evaluating it.
Yeah.
So we'll definitely get more into that. Then overseeing the implementation, making sure what gets built actually aligns with the architectural design.
It's not just a one-off thing at the start then.
No, definitely not. It's ongoing.
So that leads to the obvious next question. What makes an architecture good? Amidst all those pressures and activities, how do you know if you've landed on something solid?
That's the million-dollar question, isn't it? The sources point to a few key properties. First off, it absolutely has to meet the system's requirements, especially those really important quality attributes we talked about: performance, security, modifiability, whatever's priority.
The non-negotiables?
Right.
Right.
It also needs to be really well documented, not just code, but using clear diagrams, clear language, showing both the static structure, how the pieces fit together, and the dynamic behavior, how they interact when it's running.
And that documentation needs to be shared, right? Not just stuck on someone's desktop. Stakeholders need to see it, review it.
Absolutely critical. Visibility is key. Also, a good architecture is one that's been analyzed, maybe even formally evaluated early in the process.
Find the flaws before you've built the whole thing.
You got it. Saves a lot of pain later. And finally, it should support incremental implementation. You should be able to build like a skeleton version first.
A minimal version that proves the core structure works.
Exactly. Even if it doesn't do much functionally yet, it proves the main communication paths, the core architectural ideas, are sound.
You mentioned structure and diagrams. The sources talk about needing different views of the architecture. Like you can't show everything in one picture.
That's right. Architecture involves making different kinds of decisions about structure, and you need different ways to represent those decisions. The sources group these into three broad types of structures or views. First is the module structure. This is all about how the code itself is organized, how it's broken down into units, modules, components, classes, layers, how they depend on each other.
So the static code organization, how it looks in the repository.
Pretty much, yeah. Then there's the component and connector, or C&C structure. This view focuses on the runtime elements.
The running system.
Exactly. The processes, the services, the objects, maybe threads, and how they interact at runtime. Think client-server, maybe a publish-subscribe model, how data flows between the running parts, concurrency issues.
Got it. Runtime behavior.
And the third one is the allocation structure. This relates the software to its external environment.
Right.
Like, which software element runs on which physical machine? That's deployment. How is the work broken down and assigned to different development teams? That's work assignment. How does the software map onto the file system or hardware? It's about how the software lives in the non-software world.
So different views for different concerns and audiences.
Precisely. Helps you communicate the right details to the right people.
Okay, so architecture is that big picture, the outcome of key decisions, influenced by many factors, described through these views. Let's zoom in a bit now to the building blocks within that architecture. Let's talk design patterns.
Yes. Design patterns are hugely important. They're essentially documented, reusable solutions to common problems you run into again and again when designing software.
Like blueprints for common challenges.
That's a great way to put it. They capture solutions that experienced developers have figured out over time. Each pattern typically has a name, describes the specific problem it solves, outlines the structure, the participants, their collaborations, and importantly, discusses the consequences, the trade-offs of using that pattern.
So they make it easier to design software that's reusable, flexible, especially maybe if you're less experienced.
Definitely. They help less experienced folks get up to speed faster by leveraging proven solutions. They promote flexibility and reusability, and they really help with documentation and communication. If you can say, oh, we use the observer pattern here, everyone on the team who knows that pattern immediately understands a whole set of design decisions and interactions. It's a shared vocabulary. Plus, you're using something tested, not just making it up as you go.
Okay, but how do these relate to the bigger architectural concepts, like architectural patterns or reference architectures? Are they the same thing?
Good question. No, they operate at different levels. Architectural patterns, like, say, client-server or microservices, define the overall shape of the system, the fundamental element types, and how they interact at a large scale.
The city plan.
Exactly. Reference models might define standard ways to break down functionality in a certain domain, like this part handles data, this part handles UI. A reference architecture might combine a reference model with an architectural pattern for a specific domain, like a layered architecture for managing financial data. Design patterns are more granular. They're the solutions you apply within components or between a few components inside that larger architectural structure. They're like the blueprints for specific types of buildings or maybe standard intersection designs within your city plan.
That makes sense. Architecture is the macro, patterns are more micro, solving recurring problems within that structure.
You got it.
And patterns get categorized, right? The source mentioned purpose and scope.
Yeah, that's a common way to organize them, famously from the Gang of Four book. Purpose asks what the pattern does. Is it about creating objects, creational? Is it about composing classes or objects into larger structures, structural? Or is it about how objects interact and assign responsibility, behavioral?
Okay, create, structure, behave.
And scope asks what the pattern applies to. Does it primarily deal with relationships between classes fixed at compile time, class scope? Or does it deal with relationships between objects that can change at runtime, object scope?
Got it. An MVC, model view controller, that's a famous one people might know.
It is, yeah. It's often considered a compound pattern, really, mixing structural and behavioral aspects.
Yeah.
Its huge value is separating concerns.
How does it do that?
You have the model, which holds the application data and the business logic. The view, which is responsible for displaying that data to the user, and the controller, which takes user input and translates it into actions on the model or updates to the view.
So UI stuff is separate from the core logic.
Exactly. Makes the whole system easier to modify and test.
Okay, so the sources we looked at went into quite a bit of detail, specifically on the creational patterns. Maybe we should spend a moment there, starting with Abstract Factory, also called KIT sometimes.
Sure. Abstract Factory is interesting. Its main intent is to provide an interface for creating families of related or dependent objects. And this is key without specifying their concrete classes.
So like, I need a set of UI widgets, a button, a scroll bar, a window, but I don't want my main code to know if it's getting the Windows versions or the Mac versions or maybe motif versions.
That's the classic example. The source mentions UI toolkits like ET++ doing exactly this. Your application code talks to an abstract widget factory. You can plug in a Windows widget factory or a motif widget factory behind that interface. The application code just says, give me a button, and the specific factory provides the right kind.
So it isolates the specific implementations, makes it easy to swap out a whole family of objects.
Precisely. And ensures consistency. You get all Windows widgets or all motif widgets, not a weird mix.
Okay, what about the builder pattern then?
Builder focuses on a different problem. It's about separating the construction process of a complex object from its actual representation.
Why separate those?
You use it when the algorithm for creating a complex object should be independent of the parts that make up the object and how they're assembled. Or when the construction process must allow different representations for the object that's constructed.
Like building a complex report. The steps might be add header, add paragraph, add table, but the final output could be HTML or PDF or plain text.
Exactly like that. The director uses a builder interface to construct the object step by step. You can have different concrete builders, HTML builder, PDF builder, that implement those steps differently to create different final representations. It gives you finer control over the construction process, especially for objects with many parts.
And the source mentioned it often builds a composite structure.
Yeah, the complex object being built is often a tree-like composite structure. And it's related to Abstract Factory, but Builder focuses on building complex objects step by step, whereas Abstract Factory focuses on families of objects, simple or complex.
Got it. And the last creational one detailed was factory method or virtual constructor.
Right. Factory method defines an interface for creating a single object, but it lets subclasses decide which actual class to instantiate.
Okay, so the main class knows it needs some kind of object, like a document, but the specific type of document, maybe my specific document, is decided by a subclass.
Exactly. Frameworks use this all the time. A framework class might need to create objects to do its job, but it can't know ahead of time the specific classes an application using the framework will need.
So the framework defines a create document method,
Which is the factory method.
and the application developer overrides that method in their subclass to return an instance of their custom my specific document class.
You've got it. It provides a hook for subclasses to provide the specific object type. It decouples the framework from the application's concrete classes. The source mentions Mac App and ET++ using this too, connects parallel class hierarchies nicely.
Okay, so that's a taste of creational patterns. And obviously, our sources mention there are many others, structural ones like composite, decorator, adapter, and behavioral ones like observer, command, strategy, chain of responsibility.
A whole toolbox, each addressing a different kind of recurring design problem. Recognizing when to use which pattern is a huge part of becoming a proficient designer.
And that ties directly into designing for quality, doesn't it? The sources emphasize that architecture is really where you make the big decisions that enable qualities like performance, security, usability, especially modifiability.
Absolutely. Architecture lays the groundwork for achieving those qualities. But crucially, the implementation details have to follow through. Good intentions in the architecture diagram don't mean much if the code doesn't adhere to them.
So how do you design for a specific quality? You can't just wish for good performance.
No, you need to
Yeah.
be more concrete. That's where quality attribute scenarios come in. They translate those high-level quality goals, like the system should be modifiable, into specific testable
Like
requirements.
little stories about the quality?
Kind of.
Yeah.
Each scenario has specific parts. The source lists 6. Who or what causes something to happen? Source of stimulus. What is the event? Stimulus. What part of the system is affected? Artifact. Under what conditions? Environment. What should happen as a result? Response. And critically, how do you measure that response? Response measure.
Okay, so it forces you to be specific. Instead of high availability, you get.
You get something like an unexpected failure occurs in a critical process, stimulus, originating from hardware, during normal operation environment. The system's processing component, artifact, must recover within 10 seconds, response measure, to maintain 0.999999 LLD response.
Much clearer. And for modifiability.
Maybe a developer, source, needs to change the color scheme of the UI stimulus, affecting the presentation layer modules, artifact, at design time, environment. The change should be completed within 3 hours, response measure, with no impact on other system features, response.
Right, that's something you can actually design for and test against.
Exactly. They make the quality goals concrete and actionable.
Okay.
And to achieve those goals defined in the scenarios, architects employed tactics.
Tactics being specific architectural decisions, design choices aimed at controlling the response to those stimuli.
Precisely. They are the building blocks for achieving quality attributes. For modifiability, for example, the tactics generally aim to do a few things, like localized changes, trying to limit the number of modules you have to touch when making a change. Hiding information within a module is a key tactic here.
Okay.
Or prevent ripple effects, making sure changes within one module don't cascade unexpectedly into others. Using intermediaries like a facade or mediator can help here.
Makes sense.
And defer binding time, basically, pushing decisions later in the life cycle. Using configuration files for settings instead of hard coding them, or using plugins. That makes changes easier post-deployment.
And for something like performance, what kind of tactics apply there?
Performance tactics generally fall into categories related to resource management. There's managing resource demand, trying to use resources more efficiently, like improving algorithm efficiency or reducing the number of calls made.
Use less stuff.
Right. Then there's resource management, how you handle the resources you have, introducing concurrency to do work in parallel, maintaining multiple copies of data or computation, caching, things like that. And finally, resource arbitration, deciding who gets access to a resource when there's contention, using different scheduling policies, for instance. The sources have some nice diagrams showing these tactic categories for different attributes.
So you use these tactics, these specific design choices, guided by your scenarios, to build an architecture you think will meet the quality goals. But how do you know? How do you check if the architecture is actually any good before you build it all?
Evaluation. That's the critical next step. Evaluating the architecture is, or at least should be, a standard part of the development process. It gives you confidence you're on the right track, helps you choose between alternatives. It's way cheaper to find a fundamental flaw in the design phase than after months of coding.
Better to do it planned rather than discovering problems accidentally later, I guess.
Absolutely. The sources mentioned successful evaluations usually have clear goals, a well-defined scope, you can't evaluate everything, a competent team doing the review, and crucially, the original architect needs to be available to explain the rationale behind the design choices.
And there are formal methods for this, like ATAM.
Yes, ATAM, the Architecture Trade-off Analysis Method, is a well-known and robust technique. Its main focus is analyzing an architecture, specifically for risks related to achieving those quality attribute goals we just talked about, the ones defined in your scenarios.
So it looks for potential problems.
Exactly. It helps identify architectural decisions that might prevent you from meeting your performance goals or your modifiability goals or whatever is critical. It pinpoints risks, non-risks, things that look okay, sensitivity points where small changes could have big quality impacts, and trade-offs where improving one quality might hurt another.
Okay, so ATEM isn't about reviewing the code itself or doing system testing or just checking if the requirements make sense.
Correct. It's specifically analyzing the architectural design against the quality attribute requirements.
Gotcha. The Nightingale project example in the sources used ATEM, right?
Yes, that was a good case study. They used ATAM to evaluate their architecture, which was intended for a product line. They had constraints like using COS components and a tight schedule. ATAM helped them analyze key qualities like availability, scalability, and modularity across the different parts of their system, identifying potential risks early on.
And there was another method mentioned, CBAM, cost-benefit analysis method.
Right. CBAM comes at evaluation from a slightly different angle.
Hmm.
It's more focused on helping architects make choices between different architectural strategies based on economics.
Economics. How does that work?
It tries to quantify the return on investment, ROI, for different architectural approaches. You start with your prioritized quality attribute scenarios. Then you assign some measure of utility or business value to achieving different response levels for those scenarios. Like, what's the value of making this operation 1 second faster versus 5 seconds faster? Then you propose different architectural strategies or improvements. You estimate the benefit each strategy provides across all your important scenarios. How much utility does it add? You estimate the cost of implementing that strategy, and then you calculate the ROI, benefit divided by cost, for each strategy.
So you can pick the strategy that gives the most bang for the buck.
Essentially, yes. It helps justify architectural decisions based on their expected business value. The NASA ECS project example used scenarios like reducing certain kinds of failures, or tracking orders better, or processing user requests faster. CBAM would help them figure out which architectural changes offered the best return in improving those specific things.
That makes sense. Evaluation seems especially crucial when you get into software product lines. You mentioned Nightingale was one.
Absolutely. Product lines are a huge strategic move for many organizations. The whole idea is to leverage a common, shared architecture and reusable assets across a whole family of related products.
Instead of building each one from scratch.
Exactly. The business goals are usually things like increasing revenue by getting more tailored products to market faster, or drastically reducing development and maintenance costs through reuse. The sources cited some pretty amazing results.
Yeah, Nokia, Cummins, Motorola, HP, huge productivity gains, massive reductions in time to market.
By really focusing on what's common across the product family, you build that core platform once, very carefully. Then you define specific variation points where the products can differ. The architect's role is absolutely central here, defining that core architecture, managing those variation points, and ensuring the architecture is robust enough to support the entire product line now and in the future.
The Celsius Tech case study, SS2000, seemed like a prime example of this, transforming from custom systems to a product line.
It really is. And it highlights something crucial for product lines: maintaining conceptual integrity. Having strong architectural leadership to ensure the overall design stays coherent and consistent across all the products and variants, that's vital for realizing the benefits.
Now, switching gears slightly, building systems often involves using CO-test commercial off-the-shelf components. The sources suggested this isn't always straightforward.
No, it definitely adds another layer of complexity. When you choose to use a CO test component, you're not just getting its features, you're also inheriting its limitations, its dependencies, its underlying assumptions. They become major constraints on your architecture.
How so?
Often a CO test component implicitly assumes or even requires a certain architectural pattern. If you're trying to build, say, a message queue-based system, but you integrate a CO test component that assumes a simple request-response interaction, you can end up with a serious architectural mismatch. Integrating them can be painful.
Okay, so you need to be really aware of the architectural implications of the components you choose.
Very much so. And sometimes, to figure out tricky design questions, especially risky ones, the sources mentioned a technique called the model problem workflow. Yes, that's a very practical approach. When the team faces a particularly uncertain or risky design question, maybe, can we achieve the required throughput using this specific technology? Or, will this proposed interface be flexible enough? They don't just guess.
What do they do?
The architect and engineers define the specific question, the success criteria, any constraints. Then they build a very small, focused, maybe even throwaway prototype, the model solution designed only to answer that specific question. They run tests, evaluate the outcome, and use that information to make a better decision in the real system design. It's about targeted experimentation.
Makes sense. And looking even broader, industry standards and frameworks also embody architectural principles, right? Like the J2E/JB example.
Absolutely. That emerged because businesses needed standard ways to build complex distributed enterprise systems. The focus there was driven by quality attributes like portability across different vendors, interoperability between systems, evolvability to add features, extensibility. J2EE provided an architectural blueprint, patterns, and components to achieve those.
And then the Luther architecture case study showed something built on J2EE.
Right. Luther was an architecture for applications running on mobile devices with limited resources, but it leveraged the J2E standards on the server side. It's a great example of that architecture business cycle flowing backwards, in a sense. Instead of every project building its own isolated stovepipe system, industry standards emerge, providing common architectural solutions, and then specific applications adapt and build upon those standards for their particular needs.
Wow. Okay.
Right.
We have really covered a lot of ground here. From that constantly changing software world and why we need to think bigger, through what software architecture actually is, the influences, the business cycle, how we describe it with views, what makes it good, then diving into design patterns as those reusable building blocks, the different categories like creational.
Abstract factory builder factory method. Yeah.
Then focusing on designing for quality using specific scenarios and tactics.
Crucial stuff. Modifiability, performance.
And finally, the practicalities of evaluating architectures with methods like ATAM and CBAM, the power of product lines like Celsius Tech dealing with COS, and seeing how standards like J2EE shape things, all illustrated with those case studies woven through.
It really does all tie together. It comes back to managing that inherent complexity in software. Architecture gives you the framework, the way to structure your thinking and your system at a high level. Design patterns provide the proven, effective solutions for the recurring problems you encounter within that structure.
So together, they're like a language, a set of tools.
Exactly. A language and a toolkit for thinking about software development that goes way beyond just writing the next function or class.
And understanding these concepts, it's not just academic, is it? For you listening, it genuinely helps you contribute more effectively on your projects.
Absolutely. You can make better design decisions yourself.
Yeah.
Communicate more clearly with your team because you share that vocabulary.
And ultimately, yeah, maybe transcend just coding lines to become a more capable, more valuable engineer or designer in this, well, incredibly dynamic field.
Precisely. It's about moving from just assembling features to consciously designing systems with purpose, with resilience, with adaptability baked right in from the start.
So as we wrap up this deep dive, here's a little something for you to chew on. Think about a piece of software you use all the time. Maybe it's your favorite app, a website, a work system, whatever. Pick one key quality attribute that you really appreciate about it. Maybe it's speed, it's reliability, how easily they seem to add new features without breaking things. Now, reflecting on everything we've discussed, architecture, patterns, tactics, evaluation, what single architectural decision or maybe a key design pattern do you suspect might be most crucial in making that specific quality possible for that system you're thinking of? Just something to ponder.